Hi, this is Einstein, and this lecture is on data management in registry research. Okay, in when we're dealing with large data sets, there are bound to be errors, and these errors can be, for example, errors regarding the ID of individuals. There can be missing data, there can be contradictory information, or there can be values that are just plain impossible. Uh, these are sort of broad categories, and there obviously are errors that don't necessarily fall neatly into these categories, and it's just amazing how many ways it's possible to misunderstand each other when you're ordering data, or the people punching in the data, and you as a researcher when to misread uh, the metadata and stuff like that. So there are going to be errors, and you need to develop strategies to handle the errors. Okay, so let's start with IDs. In a data set, normally each individual should have a unique ID. One approach that's kind of common to do is to sort the data according to this ID. Uh, Often you can just look with the naked eye and see that there are problems. But if you have millions of records or rows, then it's not necessarily that easy to just look at the data and discover if something's wrong. Still, you should identify and delete duplicate rows, so rows with the same ID number. So what happens if we don't? What happens if we keep these individuals in the data where that have multiple records? If we keep all the records, well, it's kind of the same as just giving them extra weight. So one individual will be counted several times. And this doesn't necessarily cause any bias or anything, but it's definitely going to affect your standard errors and stuff like that. Now, a lot of records have missing IDs. This is very common, especially if you're dealing with data sets with millions of individuals. Then uh, thousands of them could have just missing ID. Okay, so how should that be handled? Uh, One way is to sort by other variables than the ID to see if there are duplicates. So in this case, an individual with ID 113 has maternal age 29, so the age of the mother. The gestational age at birth was 37 weeks. Weight at birth 3,400 grams. Father's age 33. Birth year 2007. Length at birth 53. And this was a boy. So this is, let's say this is from the birth registry. If we then sort according to, for example, the 3 or 4 first variables here. So you sort according to maternal age, gestational age at birth, weight at birth, paternal age, maybe even birth year, or maybe sort according to all of these. Then we can see that they all match. And this is probably because they're the same individual, right? It would be quite the coincidence if two individuals were born with parents who were exactly the same age and they weighed the same to the gram and had to the centimeter the same length at birth, right? So we should see if there are duplicates, or we can detect duplicates by using the other variables. We don't necessarily have to rely on the ID alone. So these guys should, if there are duplicates, these guys should be thrown out too, right? If we are only dealing with one register, then we should keep records with missing IDs that are not duplicates, right? Because they're just another record. If we have several registers that we need to merge, then we have to have the ID. So by necessity, we very often or mostly end up deleting records with missing ID. Now, I say there are thousands of these records in a lot of data sets, but if you have 3 million observations or 3 million individuals in your data, then 3,000 is just 1 per 1,000, right? So we have thousands because the number of individuals is so huge. So this is, in one way, it's a small problem. In another way, it's a big problem. So lots of individuals, but a small proportion. Next, we'll look at missing data and how to handle that. And what I always do is to summarize missing values for each variable, at least if I have a number of variables that is easy to handle. If I have 200 variables, I don't necessarily look at the number of missing values for each variable, but maybe I would summarize and then sort them according to the number of missing variables so that I know which variables have lots of missing values and which variables do not have this problem. One approach to handling missing data is to just delete records with missing data. And that can be risky if the number of individuals decreases by a lot. So, for example, if you have 2 million individuals in your data and then you have 200 variables, and then you delete everybody with missing on at least one of those variables, then maybe you're left with 500,000 individuals. So that's a problem, right? It's not as risky if the number of individuals is still very large. So if you have 3 million and then you end up with 2 million or something like that, you don't lose all your power, for example, and especially if you have reason to believe that the observations are missing completely at random. That's MCAR, missing completely at random. And that corresponds to rolling a die. So if you can imagine that, for example, somebody's punching in numbers and once in a while they just skip a cell in an Excel sheet or something like that, then there's no systematic way that these errors are occurring. And that would correspond to just sort of removing your data, removing some of the individuals at random. And that's not going to introduce bias in any way. It's going to affect your standard errors, but if you're left with 2 million individuals and you don't have any reason to suspect bias, then it's still going to you're going to be fine, probably. A better way to handle missingness, at least if you have lots of missingness, is to just model the missingness. For example, if you have an individual with missing on sex, but you know that the height is 195, then this is probably a male, right? Because you know that the proportion of individuals that are 195 or higher or taller that are male is just overwhelming, right? So it would be a shame to throw out that whole individual just because you're not 100% sure that it's a male, because you're 99.9% sure. one way to model missingness is multiple imputation, and that is when we replace the missing observations by predictions based on other variables. So for example, with the height example, if we had the height of most of the other individuals in the data, then based on these heights, we could predict what's the probability that an individual with a height 195 meters is a male or a female. And then after we do this for all the missing variables, then we generate several imputed data sets. So an imputed data set is a data set where we have sort of guessed. In some cases, we're going to have little information, or it's going to be like a coin flip, right? Maybe it's a male, maybe it's a female. We don't know, based on the other variables, for example. Still, if we do this a lot of times, so we generate not one data set, we generate maybe 100 or at least 20 data sets, then we, on average, we're going to not be completely wrong. And then we perform our analysis. If that's a regression analysis, for example, we just perform the analysis on all of these 100 sets that we created on the imputed data sets, and then we combine the results at the end. And this requires missing at random or missing completely at random. So missing at random would be, for example, if males, if we have missing on a depression score, and that's more prevalent among males because men are not good at talking about their feelings, for example. So then they would have missing on the depression score, and it would be because they're males. So it's not missing completely at random. Missing not at random would be if they had missing on the depression scores because they were depressed and they just couldn't sort of summon the energy to answer the form. One example there is that's probably not missing not at random, is when you ask pregnant women if they're smoking or not. Then you have a lot of women who say no, then you have those who say yes, and then you have those who say, I don't want you to ask me that question. And if you're in that category, I don't want to answer that question, a lot of those women are smokers. Okay, and we can see this in the data, and I'll get back to that. We could also use maximum likelihood. That would mean that we assumed the distribution of missingness somehow, and then we build this distribution directly into the model. It's not as common as multiple imputation, and that's because you have to program each scenario individually, or at least there is no general software that I'm aware of. So most people just use imputation, even though maybe it's more it takes more computational power from your computer. People prefer it because it's a standard way you can do things, and you can do the same thing every time. One advantage of using maximum likelihood is that you're going to get the same result every time you run your analysis, and you're not if you're running multiple imputation, because every time you generate these 100 data sets, they're going to be different from the last time you generated 100 data sets. So you may have that p-values or standard deviations or estimates are jumping a little bit up and down. But if you use maximum likelihood, you get the same result every time. One way to handle missing values is to just keep it in and just say, well, missing is its own value, or it's its own category. So you have yes, no, or and missing, for example. And like I said, smoking status for pregnant women, yes, I'm smoking, and missing have very similar characteristics and other variables. So you can, for example, you can compare birth weight, and then you see that the birth weight among those who say yes and those with missing is very similar, but the birth weight is different in these groups from the birth weight among those who don't smoke. So that's and if you look at other variables, you can look at socioeconomic status and stuff like that, and you can see that they're more similar among yes and missing than they are among no and missing, or no and yes. So this is a good strategy, I think. Just keep it in. These guys had missing. Just instead of yes and no, you're now you have yes, no, and we don't know.